So big pleasure to have today at the Game Theory Seminar at Mathematical Game Theory Center in Rabat, Guillaume Carlier, who was teaching all this week, Optimal Transport, his second visit to Morocco, and we are very proud and happy to have him doing these efforts. And so Guillaume, I know him since we've got our PhD exactly at the same year, same time, and since then we follow each other's work, and we have been colleagues also at Dauphine for many, many years, and he's key in the collaboration we have with Dauphine, because the first year of the PhD program, the pre-doc year is also a master with Dauphine University, and Guillaume is following this and supporting this, and without his support you would not have gotten this collaboration. So thank you, Guillaume, and I give you the floor.
Thank you very much. So thank you, Rida. So it's a big pleasure to be here. It's my second time at UMC Spain, Rabat. I've been to Morocco many times, and it's always a pleasure, of course. And okay, so I'd like to. So sorry, maybe you're fed up with optimal transport, but we still have a few lessons. It's just it may look like an obsession because the talk I'm gonna give today is about some extensions. Take it as an overview of what can be done in terms of generalization and also in terms of computations of the solution of optimal transport problem in a broad sense. And it's taken from a recent joint work with two of my former PhD students, Hugo Malamud and Maxime Sylvestre, which maybe the key words are weak optimal transport, I will explain what it is, and the presence of extra constraints, which make the problem slightly more challenging and non-classical, which I will call moment constraints, okay? So to start with, maybe it's good, so there's a lot of jargon in my title. Let me start with a small tour of a zoo of optimal transport problems, right? So there is what I'm teaching this week, right? That's so-called vanilla optimal transport of Monge-Kantorowicz. So the problem is the following. You have a distribution of sources, mu, and some space, some distribution of targets given by probability measure nu, maybe on another space, a cost function. So C of xy is the cost of transporting one unit from x to y. And what you want to find is an optimal coupling, which will be denoted pi here. So it's a probability measure on the product space, whose first marginal is mu and second marginal is nu, so it's mass conservation, which makes the average of the cost as small as possible, right? So this is linear programming possibly in infinite dimension if x and y are infinite. But still, it's in terms of existence, for instance, it's quite easy to see that for weakened topology, the set over which you optimize is compact, the cost is continuous. So existence can be taken for granted. And there's also a nice thing which was observed by Kantorowicz a long time ago, and probably one of the reasons. So I mentioned this during the class, but Kantorowicz should be mentioned because it's probably something which is not so well known in the West, but he invented duality for linear programming, really, independently and prior to what was done in the West. So, okay, what Kantorowicz discovered is that the previous problem has a value which is the same as that of the so-called Kantorowicz dual, which consists in finding two potentials, phi and psi, which you can think of as being some sort of Lagrange multipliers for the marginal constraints, which make the sum of these two integrals, the expectation of phi against mu plus the expectation of psi against nu, as large as possible, but there's a constraint, they cannot be too large. And these constraints say that phi of x plus psi of y is less than the cost, okay? And this problem as well has a solution. I don't want to get too much into this, but there's not, actually we're gonna see the details of what I'm telling here tomorrow in the class. Even this problem, even though it's a bit complicated to optimize over continuous function, it's not probably a not very nice space. But in fact, you can convince yourself that there exists a solution to this dual. And what duality tells you is that optimal plans are concentrated on the set of pairs, complementary slackness, on set of pairs and x and y, for which this inequality is slack, is an equality, right? So it's concentrated on a set which presumably is small. The optimal transport should be sparse in the sense that it should concentrate on a set where a certain function achieves its maximum. Okay. So I don't want to get too much into this. It's regarded now as a classical theory, textbooks and so on. In fact, it's not so easy to solve in practice linear programming in large dimension or infinite dimensions. And as being linear programming, it can be a little bit unstable. You change a little bit the data. It's not clear how to follow a solution moving along a parameter and so on and so forth. There can be suddenly the appearance of multiple optimizer. So, okay, it's regarded as a reasonably difficult problem to solve numerically, for instance. And of course, you can use a simplex algorithm, or network simplex, or things like this, but it's limited to small instances. So one of the reasons why people have introduced some regularization in the problem is because this problem is difficult to solve numerically. So here he enters the realm of what is called entropic optimal transport. It was made popular. It's an old idea, by the way. It even goes back to some work of Erwin Schrödinger in the 30s. So the idea is it's the same as before. You've got the transport cost, C, same constraint, transport plans, but you have a parameter epsilon, a sort of regularization, and you add epsilon times the relative entropy of the plan with respect to the product measure in the optimization criterion. Okay, so what is nice with adding an entropy is, first of all, it makes the problem strictly convex, so there is a unique solution. And since you add the entropy, you force the plan, which typically the optimal plan in optimal transport is sparse. Imagine that you're in dimension RD times RD. Typically, the support of the optimal plan is a manifold of dimension D in dimension 2D. It's a sparse object. Here, you force the plan to be diffuse. But what is nice is that the optimal regularizer, the optimal plan by epsilon, it has a density with respect to the product measure mu tensor nu, which is in exponential form. Okay, it is in Gibbs form. So it's given by exponential of minus this guy divided by epsilon. So it's typically something which is very concentrated when you're away from the minimum of this function, okay, times the reference measure, which is mu tensor nu. So first of all, it's parameterized just by a function of x and a function of y, so the dimension is really smaller. And if you want to, now the task is not optimization anymore. It's find the potential phi inside, just a function of one variable, such that this guy has marginals mu and nu, meaning that when you integrate with respect to the y variable, you find mu. It's this equation. So if you know the psi, the phi epsilon is in closed form, okay? It's a log Laplace transform of something. And likewise, if you know the potential phi epsilon, you know the potential psi epsilon. So you want to solve this equation, and this gives rise to a famous algorithm, which is synchron. You iterate over these two conditions. And there are lots of results which say that it converges, even with some rates in some regime and so on. It's been actually it's an old idea for LP, not only transport. There was a very nice paper by Roberto Cominetti and Jaime San Martin, who consider anthropic penalty for the joule. So it's the same as adding an entropy to the transport problem, and it's been discovered many times. It has some connection with stochastic analysis, large deviations. If you know a little bit about large deviation theory, good rate functions, this log Laplace kind of functions arise naturally. Okay. But in practice, you see in discrete, for instance, if nu and mu are discrete, you see that looping over these two equations is 2 lines of code, and it's a remarkable thing that it converges linearly to some extent. Fine. Continue the tour of the zoo. There is the so-called martingale OT problem. I don't know if Nizar mentioned this here when he visited you at some point. No? So did he mention martingale optimal transport? He's one of the founders of the domain. So the problem is the following. It's a problem that has its roots in math finance. And imagine the following problem. It's a problem of pricing. It's very financial engineering, if you want. imagine that you're interested in giving a price for an asset that pays a certain payoff, C of xy, and x and y are, let's say, a certain state, let's say a stock price in future dates. Okay? Let's say tomorrow and after tomorrow. Okay? And what first principles for mathematical finance tell you, basically no free lunch or arbitrage theory, is that the value of such a special case of an exotic option should be the expectation of the payoff under a probability which has nothing to do with the historical probability, which is called a risk-neutral probability, which makes returns a martingale. Okay? This is something like abstract, but this is something which you can recover from market data. For instance, if you read the financial press, and if you look at the price of European options with different maturities and different strikes, you can reconstruct the law. If you know the expectation of x minus k plus for every k, from this you can reconstruct the probability distribution of x. That's the idea behind this. So mu and u are the law of returns in future dates. I put 2 dates, but there could be more, right? It's just to make the thing simple. If I were Nizar, I would have immediately jumped into the continuous time and so on, which I will refrain from doing. And but the point is that in general, the risk-neutral probability may be not unique, and in fact, you need a model to estimate it. It depends. You have diffusion model. Maybe there are some coefficients you don't know in the diffusion. A bank, a financial institution is using one. Another one is using another one. They are doing some numerics. They fit to the data and so on and so forth. So robustness or robust finance would like to have information on prices which are kind of independent of the precise model you have on the whole risk-neutral probability, which, by the way, may be not unique as well. Okay, so that's what it says here. So the idea that was proposed, okay. Ah, non, alors I'm stuck. Je peux avancer avec mes doigts. Je ne peux pas marcher comme ça. Ah, ok. Okay, so the idea is not to try to compute really a price, but to have an interval. And you know that the price for an option which pays C of xy, if the price tomorrow is x and the price after tomorrow is y, should be the expectation under some probability, whose marginals are mu and u, as in optimal transport, because it's what you reconstruct from market data. And on top of that, it should be consistent with arbitrage theory. So it should be a martingale. So certainly you don't know exactly, there may be many of these guys, okay? But certainly the price you should, alors, attends, mais comment? Okay. The price of the asset should be something between the mean and the max of this quantity among measures on R times R, or it could be multidimensional as well, for fun or for financial purposes as well, having prescribed marginals, but also pi should be the law of a martingale. Okay? So what does it mean? It means that if you see, so pi as first marginal mu, but you can say that pi x is the conditional law of y given x, induced by pi. It's the law of the stock after tomorrow given that of tomorrow. Being a martingale says that the average of this pi x should be x. Okay, it's a sort of fair game. In average, you don't gain anything, right? Alors, je réessaye. Non. Fine. So maybe let me introduce a notation. So if pi is a measure on the product, I denote by pi x the conditional probability, the kernel, the transition kernel from date tomorrow to date after tomorrow. So saying that pi is a martingale says that almost surely the expectation of y given x induced by the plan should be x. Okay. So it attracted, it started, I think it's fair to attribute the financial motivation to people you know, actually. Nizar, Alfred Galichon, Pierre-Henri Labordère, who is famous quantitative researcher in French banks, but also some mathematicians who are attracted for fun for this problem, like Julio Bakov, Matthias Beigelberg, Nassif Goussou, maybe you know him. It has nothing to do with math finance. It's more, yes? Yes, mu almost surely it's unique. Yes, yeah. Okay, and it has some regularity. I don't want to get into this, but these conditional probabilities are well defined. Okay, there's no ambiguity. So here you face something different, right? A different constraint that, yeah. First of all, there's a first difficulty that it is not always the case that if I give you two measures on the real line, you can find a martingale whose marginals are mu and u. In some sense, if you think in economic terms, in terms of risk, the time being, the risk is increasing. So for the existence of a martingale plan, you need some special properties of mu and u. And these properties are known, and maybe I can explain, right? Imagine that mu and u are the marginals of a martingale whose law is denoted by pi. Now take a convex function j. You compute the average of j at the terminal time, the integral of j d nu. Okay? Well, you use the Tower properties. It's an expectation, so it's the expectation of the conditional expectation. But if j is convex, this guy is larger than j at the conditional expectation. It's conditional Jensen, right? But if it's a martingale, this guy, this conditional expectation is x. So you see that if you take a convex function, the evaluation against nu is larger than the evaluation against mu. In some sense, the risk is increasing, passing from one date to the next one. So it means that the measure mu and nu should be in the so-called convex order. Okay? In 1D is very famous in economics. I think there's a famous paper by Rothschild and Stiglitz, how you pass from one measure to another so that risk is increasing. This is the same kind of ideas. In fact, it's much older, I have to say. The first paper that proves, so it's necessary for the existence of a martingale that mu and nu are in the convex order, but it's also sufficient. Okay? This is a classical result, which was first proved by French mathematicians, Pierre Cartier, Fell, I don't know his name, and Paul-André Meyer. And people in math finance, I don't know why, they always quote Strassen, who is German, but who wrote a paper later than, it's slightly more general, but the idea is very much in this paper by Paul-André Meyer, who was a great French probabilist. Okay, so there's a caveat here that this problem may have an empty admissible set if mu and nu are not cooked up in the convex order. And also from a practical point of view, I want to stress if the theory tells you that the time marginals should be increasing in the convex order, when you do numerics and you approximate the measure, you quantize or you use sampling or whatever, or Monte Carlo methods and so on, when you discretize measures in convex order, you have no guarantee that you stay in the convex order. So you can imagine that it's a bit tricky to discretize things, to approximate the problem, which remains the essence of the constraint, which is in this martingale OT problem, right? Nevertheless, okay. It's very tempting now to say, okay, I have an extra constraint that the integral of y minus x, now pi is denoted gamma, I'm sorry, should be 0, so I add a Lagrange multiplier, as I did for optimal transport, vanilla optimal transport, and to introduce this sort of Lagrangian, okay? And the dual variables are alpha, phi, and psi. Phi and psi are Kantorovich potentials and the vanilla theory. But alpha is more tricky. It's a Lagrange multiplier for the martingale constraint. And you can ask yourself whether the inf sup and the sup inf are the same. Is the sup inf well posed, and so on and so forth. And the sup inf consists in maximizing the same guy as in the Kantorovich dual, but you add an extra term which vanishes along martingale. Okay, it's an increment of a martingale. So when you integrate against pi, this disappears. Okay, this seems a very harmless modification of vanilla OT, and it is not. In fact, it turns out, and it was noticed in particular by Nizar, but also people like Nicolas Juillet, that that in fact existence of reasonable Lagrange multipliers for the martingale OT problem cannot be taken for granted. Okay, that's not even in large classes like L1 function and so on. And this counterexample arises even in dimension 1 with simple distributions. Okay, so it's fair to say that it's both from a theoretical but also computational. It's a quite challenging problem, this martingale OT problem. Okay. So let's continue the zoo. I started with standard vanilla OT, introduced entropic optimal transport, then this martingale problem. I say it can go on forever and so forth. But at some point, there are things which behave nicely. Okay, yeah. It's this bunch of authors, Nathalie Gozlan, Roberto Sanson, Cyril Roberto, and Prasad Tetali. They introduced a generalization of the optimal transport problem, which has as particular cases all the cases before. They just had the bad idea that they called it weak OT. To me, it's stronger than OT because it's a generalization. And this generalization goes like this. It's a sort of nonlinear version of the, I said in the beginning that optimal transport is linear programming. Here the idea is a bit different. You minimize the cost over couplings between mu and nu, same as before. But now the cost is a function of I, x, and of the conditional probability. So typically it's a convex function of pi x, but it need not be linear. Okay? So if we look at standard optimal transport, well, this capital C, what is called the weak OT cost, is just the integral of the cost with respect to the kernel, and then you integrate with respect to mu. So it's linear. The entropic, there's a property, there is also a sort of a tower property for the entropy, you know. The entropy on product spaces can be written as an average of an entropy of these integrations. So entropic OT is the same, so it's same cost as before, but you add epsilon times the entropy of Q. Pay attention to the fact that Q plays the role of pi x against the second marginal. And martingale OT, of course, it's the same, so you have the cost, but now there's a constraint that pi x should have the center of mass, which is x. So you introduce these constraints, so it's the cost if the average is the right one, and plus infinity otherwise. Okay? But there are plenty of other examples. I don't want to go in the... There are plenty of other examples. And typically, sorry about that, this is what I will call a hard moment constraint. Okay? You have the prescribed marginals, but also some conditional quantities are prescribed. The expectation of some functions of the future given the present is given. Okay? As in martingale OT. Sorry? Yes, it will be an essential. In all these examples, this is the case. The case of non-convex is more tricky. You have to relax, and there are things. Okay, but in all I'm going to say this will be convex in C. It's really an essential thing. But also you can also consider more gentle costs. For instance, instead of imposing that the integral of y d pi x is x, you could penalize and say you pay a large constant times the square difference between this. Okay? So here, this is a so-called Martin cost. This is something that has been considered also by people like Talagrand to consider some functional inequalities. Probably you know the name of Talagrand. And it's another class of weak cost where you take a conditional expectation and you pay some convex penalty. So theta is a convex penalty. Okay? So for instance, if you want to make the hard martingale problem soft, you can add this penalty and put maybe a large factor in front of it. Okay? And that's it. So there are plenty of examples, and now I think I can. It's nice to have this general viewpoint, in my opinion, because it's you see what's going on, you see the structure and what is needed in a broader way. So okay, so this was a long introduction, but to give you an overview, what I'm going to do is define a little bit our results with Hugo and Maxime. I'd like to discuss the Martingale case because we have my background is very much from variational analysis and optimization and convexity. So I'm kind of obsessed by qualification condition or stability of optimization parameter with respect to a parameter. So it has very much to do with this. So I will introduce some moment qualification constraint which does the job, for which you can take for granted the existence of a dual solution. Okay, so I'll discuss the Martingale case. This probably I won't have time, and I would like to finish with some numerical results, which are not only numerical results. They rely on some approximation with some entropy, a la Sinkhorn, but to analyze the convergence of these algorithms, you really need the kind of theorems I would have presented before. Otherwise, you have no guarantee that it approximates correctly the problem you want to solve. Am I clear so far? Yeah. Okay. It's kind of working randomly. Right? Sometimes it works. If it never worked, it would be reassuring, right? I never use it, but sometimes it works, sometimes it does not. Okay. Okay, this is not so important. Okay, so the data of the problem will be the following. In fact, in the paper we analyze more general situations, but I don't want to be too precise. So the problem will involve 3 ingredients: a transport cost, of course, given marginals. So you optimize something among probability measures with given marginals mu and nu. There will be the hard part will be this one. This will be a function j. And there will be a moment constraint that I enforce the transport plan to have that the conditional expectation of j vanishes. For instance, in the Martingale constraint, g of xy, you are in an Euclidean space, it's x minus y. And the Martingale constraint, that the integral of this guy against pi x is 0 or mu almost surely. Okay. But I can also consider other moments which are going to be penalized by a soft convex function, a continuous convex function, theta. Okay, so this I will call hard moment constraint, and this I will call soft moment constraints. Okay, so this is I mentioned the costs introduced by Marton. They fit this thing, and the Martingale case fits this the second line. Okay, so sorry, it's a bit technical because I have to describe all the ingredients. So the problem of interest is this type. So it's to minimize a cost depending on the transport plan pi. So what I minimize, there's a vanilla tipped cost. There's a convex penalty of some moment given by the map F. But now what is nasty is a constraint. Pi should be in this set which I denote like a G orthogonal, which is precisely the set of plans for which this guy is 0, right? Of course, I will assume that there are feasible plans which make this integral 0 almost surely, otherwise the problem is silly. The feasible set is empty, okay? So if you do so, the existence of a minimizer here is not very difficult. The problem is how to characterize it, and are there Lagrange multipliers for these guys? This is what I want to stress. And do they have good properties? You know, for quantifying the size of Lagrange multipliers tells you a bit about the stability of the problem. So this is one thing. And in fact, a problem like this you cannot really solve numerically. There are good algorithms. So we want to go also to the entropic version. Sorry about this. And also we want to analyze what happens when epsilon goes to 0 precisely. So it's the same as before, but for stability purposes or computational purposes, on top of this, I add an entropic term, just as in the Sinkhorn problems, right? And of course, what I will need is that not only there exists a feasible transport plans, so which satisfies the J constraints, the moment constraint given by the function J, but also that such a plan with finite entropy exists. Okay, it's more demanding. Now I'd like to describe the dual side of this problem. So we can guess what are the dual variables. Okay, we have how much time do I have? I'll stay okay, perfect. So there are the usual suspects, which are like Cantor-Rovich potentials, which are phi and psi, function of x, function of y, which are Lagrange multipliers for the marginal constraints. So more or less, we are confident, but we know how to treat these guys. There are Lagrange multipliers associated. You can dualize the term with the theta, so you're confident that if theta is convex and continuous, there will be an element in the subdifferential or something like this, which will be this lambda. This is dual variables for the soft constraints, and the nasty guy is this one. Okay, fine. Nevertheless, what you can do is to try to write this in soup form. Think Lagrangian in Lagrangian duality terms, right? It's always good in my as a starting point for duality in convex optimization. So, okay, all the dual variables I denoted it's a quadruple, right? It's a bit complicated, but yes, and somehow they augment the initial cost. So, as in Monch-Cantor-Rovich, let me introduce notation. So, a direct sum of a function phi O plus psi is a function of x and y, which is phi of x plus psi of y, and I have also to multiply the moment map f and g by multiplier. So I denote it by O dot, but it's pointwise multiplication. And you see that the multiplier, they only depend on x. Okay? So you can think in terms of standard vanilla OT, provided that there is a shadow cost which depends on multipliers, which is augmented by these guys. Okay? And that defines a certain operator, it's linear, lambda, which is the shadow cost minus this guy. Okay? And I can define a function of the dual variables, or the Lagrange multipliers if you want, which is, there is a dual term for the penalty, so this is theta star of lambda. This part is very classical. And there is this part, which is as in Cantor-Rovich duality, right? There's a price given by the multipliers for the mass conservation conditions. Okay? Fine. The problem, let me describe the, okay, I didn't show the dual, sorry about that. So the formal dual of the problem without an entropy is minimize this guy subject to the constraint that lambda psi is non-negative, right? If I was in the vanilla world, they would not be there, it would be standard Cantor-Rovich duality. Okay. No, because there is a minus here. I prefer to minimize, but that's kind of a convention, right? With an entropy, you can play the same. Oh, okay, it's here. So by duality, you can prove that the minimum of the initial problem coincides with the soup of minus f. So, okay, my slide agrees with your, has the same taste as you. But I don't like to maximize the negative. I prefer to minimize, but it's okay. So you see there's a constraint, and there's this convex function, which is here. In the entropically regularized version, what happens is that this hard constraint on the Lagrange multiplier is not present. There is an exponential penalty. So instead of having a constraint, you got the same functional which is here, and it's augmented by something. You pay an exponential penalty, okay, if lambda has not the right sign. Okay? But sort of softer. you pay something exponential if the constraint is not satisfied. Of course, here if I use Fenchel-Rockefeller theorem, I need spaces to be in duality, right? To be dual to each other. So it's true that spaces of measure are in duality with spaces of continuous functions, but there's absolutely no reason, and it's totally false to hope that the Lagrange multipliers for the hard constraints will be continuous function. Okay? Think of a problem depending on a parameter, problem with constraints. There's no reason why, in general, the Lagrange multipliers will depend continuously on the Lagrange multipliers, unless you make crazy assumptions. Okay? So what you can do is relax a little bit and replace, in terms of the variable y, everything which should be continuous will be continuous. But in the dependence with respect to x is a bit nastier, and the dependence of the moment constraint on the x. So every Lagrange multipliers which depend on x, I replace continuous by just bounded, L infinity. Okay? And then lambda xi is not a continuous function anymore, but it's sort of a mix. It is measurable and bounded in x and continuous in y. So it's okay to give a meaning to this. So this is duality, but so far we have no clue about the existence for a minimizer here and a minimizer there. And as I told you, in martingale, it's known as a tricky problem. Yes? Compact metric, let's say, okay? Compact and metric. It's quite general. And F and J are continuous, okay? But Laue semi-continuous could be considered. So the Laue semi-continuous situation could be considered as well. But here, I'm this design, I'm this setting. Okay. So the task, you will have to work by hand to understand why a problem like this has minimizer or maximizers. And the first act to understand it is why, if you take a maximizing sequence, it remains bounded in some. The problem doesn't want some of the potential, some of the dual variables to be large. It's really what we have to understand. Okay. Okay. So first of all, there's a nice guy. I told you there are soft moment constraints, which have been dualized by dual variable lambda. If I make theta continuous and f bounded, in fact, you only see theta behaves like a globally Lipschitz function, so you can bound a priori the lambda part. So in the Lagrange multiplier, there's phi, psi, alpha, lambda, but the lambda is not an issue. You're pretty sure that you can restrict yourself to something which is bounded in an infinity a priori. Okay? So this, you can forget about the lambda and the weak cost. So it's just an observation. But the problem is that the troublemaker is alpha. So that's why we introduced a qualification of the moment constraint condition, which says the following. So first of all, it's sort of a normalization. It says that the constraint G, in average, is satisfied by every plan. Martingale, it is true, right? If there is a martingale plan, mu and nu have the same moment, so against any transport plan, the integral of y minus x d pi is 0. And now there's something which looks more like a qualification condition, right? Which is the following, which asks that not only you can find a plan with marginal mu and nu which kills the moment, but you can also find one which has prescribed moments which is close to 0 in L infinity norm. So what do I mean? I mean that there is some small eta such that for every r, which would be a perturbation, instead of solving the problem with integral of g equals 0, you want to solve it with integral of g equals r. So it's a sort of openness condition, if you want. I will explain in the martingale case what this condition means. Provided that r is sufficiently small and it is 0 mean, right? You can find a plan such that the corresponding conditional expectation is this function R. Not only you can reach 0, but you can reach some sort of neighborhood, but it's very constrained neighborhood. It's for L infinity norm, right? Of 0. Okay. No. And measure mu and u. There's an interplay between mu and u. G is not really too sure, but if G is 0, you can forget about if G is G 0, you can not do that, but in fact, you can forget about the constraint. Yes. And also, yeah, and if it's a bit tricky, you can reduce dimensions, for instance, right? If some projection should be 0, it means that everything is happening on a smaller dimensional space. I can do refinements here, okay? So it's a strong condition, but qualification of a constraint is a strong condition. Pay attention to the fact we are not in the usual setting, we are in infinite dimension, and playing in problems which appear as problem of optimization of our measures. So, okay. This is a bit technical, but okay. But if we do that, our main result is that both in the regularized and non-regularized case, there are optimal Lagrange multipliers. So not only the primal and the dual have the same value, which is guaranteed by Im-Soup kind of theorems of Fenchel-Rockefeller. I mean, it's more or less the same. It's a matter of taste. But there is no guarantee that there are conditions. And pay attention that not only there exists an alpha Lagrange multipliers for the moment constraints, but it is bounded. Okay? So now that we know that there is an optimal psi, which is all this awful phi psi lambda alpha, we know that a pi is optimal if and only it is feasible, and it satisfies the primal dual relation, which is here, which exactly means that, remember that here epsilon, in this slide, epsilon is 0. Lambda psi, this complementary slackness, should be 0 pi almost everywhere. The multiplier, well, the dual variable for theta should be in the subdifferential at theta evaluated at the soft moment map. And the first condition tells you that alpha is really a Lagrange multiplier in the usual sense, in the historical sense of Lagrange, in the sense that the alpha which is here is such that, if you know it, solving the constraint problem is the same as solving the unconstrained problem, adding this penalty. Okay? And the size of this penalty, it's part of the theorem, is bounded. And you can compute some bounds. So this is for the unregularized case. And there's a similar characterization for the regularized case with an epsilon. So now pi is not something which is supported on the 0 set of the function lambda psi. It's a Gibbs measure. It has this form. It's more explicit. Okay. Lambda psi is explicit in the Lagrange multipliers. The Lagrange multiplier, the dual variable lambda, satisfies the same condition as before. Okay. and of course, here, if you know psi, you can solve the potential phi m psi by using Sinkhorn algorithm here. Okay. And exactly the same Lagrange type of result that the alpha which is here gives you the information. What I'm claiming here is that if you know the good alpha, you know how to solve this problem. Okay, that's the point. Okay, so here is this is more or less our main result. From this, you have some consequence. I don't want to get into like the convergence as epsilon go to 0 from the regularized to unregularized. We have also situations where you would like to approximate hard constraint by soft constraint. Yeah, we do. We do. We even have rates of convergence. Okay, it's something like for the value it's in epsilon log of epsilon times the L infinity norm of alpha. No. It's well. Yeah, but okay. In fact, you have to use the dual. It's more or less tools of so-called gamma convergence. Its problem it depends on parameters. You compare the tricky part. Okay, it's a technical question. The tricky part for entropic regression is that, of course, the true minimizer need not have a finite entropy. Here, there's an entropy here. So you have to understand the cost of approximating an arbitrary measure which satisfies a lot of constraints. Even in the case of marginal constraints, it's hard, but here we have extra constraints. What is the cost of regularizing without violating the constraint with a reasonable entropy? The entropy typically blows up, but at which rate? Okay. So there are techniques to do this. I've been working on it for many times. There's so some techniques which are called block approximation and things like this. It's a bit of technicalities, but believe me, it's true. Okay, so I'd like now to explain. It's a bit hard to swallow. There are lots of problems, so sorry about that. To explain what this qualification of constraint means in the case of the martingale constraint. So in the martingale constraint, you know that for the problem to make sense, you need the marginals to be in the convex order. And I mentioned that it's what makes the problem, even from a practical viewpoint. I give you measures, let's say Gaussian with the same center of mass but different variances. They are in the convex order, but when you discretize, if you do it very naively, maybe you lose the convex order. So you want to solve an easy problem which at a continuous level makes perfect sense. Once you discretize, just the feasible set is empty. So you should pay attention to this. Okay, so our condition in the setting of martingale optimal transport, where J is just x minus y, or y minus x, is that if you're in a small L infinity ball around 0 of function r which are centered, the center of mass is 0, the integral of r is 0. Each time you have a guy like this, you can find a plan whose average is not only x, but x plus this perturbation. Okay? So what does it mean? And maybe I have to enter a little bit about what is known and what are the classical assumptions people do in martingale optimal transport. But before this, I'd like to introduce a notion of stability of the convex order constraint, which we introduced in the paper and which appears unrelated, but you will see it is related. So I will say that a pair mu nu is W infinity in the convex order is W infinity stable if when you make a small perturbation, in a sense I will precise of mu, without changing the average, the corresponding perturbation, they remain in the convex order. So it's the stability of the convex order. So I said that there is a ball centered at mu for the distance which is W infinity. So what is W infinity? It's very conservative. In mass transport, typically what you do is you minimize the average of the distance, or the distance squared, or the distance to whatever power you want. Here, you're not minimizing the LP distance, you're minimizing the max. So the W infinity distance between P and Q is the minimum of our couplings between P and Q of essentially the supremum of the distance on the support. Okay? So it's very conservative. Perturbation you can do in W infinity distance are very, very, very constrained, very rigid. Now, of course, it's not very difficult to see that our notion of stability implies the moment qualification of the constraint in the case of martingale constraint. So our condition is weaker than W infinity stability, but still it's an abstract notion. So now let me introduce two notations which are very important in martingale optimal transport. One which is important, the other is more technical. The first one is called irreducibility. And irreducibility of a pair mu nu in the convex order means that not only I can find a martingale, where there's mu and u, but I have to find a martingale where the kernel, pi x, is equivalent to nu almost surely. Which means that, yeah, in fact, you can find it's irreducible in the sense of irreducibility of Markov chains, if you want. It means that you can states which are charged, they can communicate even through a martingale, right? So irreducibility means I can find a kernel, okay, which is a martingale, and such that pi x and nu, they are equivalent and say that they have the same negligible set. Think that anyway, a condition like this, I will need for sure when I add an entropy. I add an entropy, so I have the entropy of pi x with respect to nu. I want this guy to be almost surely finite. And if I need this, I need that there is a martingale, which at least has a density with respect to nu. Okay? So it's not at all, it's clear that conditions like this play a role to make the martingale OT problem well conditioned in some sense. And there's another condition which is called non-degeneracy, which is that the support of mu, not only if mu is in the convex order, is dominated in the convex order of mu, it's quite clear that the support of mu is included in the convex hull of nu, but here, of the support of nu. But here I need more, I need that the support is not only the support, but a neighborhood of the support is still included in the support, in the convex hull of the support of nu. It means I can add a little bit of diffusion and still satisfy the constraint. Okay? Now you must be fed up with definitions and so on. Ah, qu'est-ce que j'ai fait? Ah, très bien. Ok. Non, pas très bien. Okay. So just to mention, probably, yeah, maybe there are construction using Brownian motion and diffusion processes of martingales built on either on stopping time, but built on Brownian motion kind of models. Maybe Nizar mentioned this. This is Bas martingales idea, which was developed by the group of Vienna around Walter Schescher-Meyer and others. And for sure, for their construction to work, they need these kind of conditions. Okay. And now I want to state, to explain a little bit the main maybe motivation of what we have done, is that in fact the stability is equivalent to irreducibility plus non-degeneracy. And since W infinity stability implies qualification of a constraint, it means that there are Lagrange multipliers which are bounded. Okay? And since these conditions are very classical in the literature, it proves, and it generalizes, even for the martingale case, this theorem is new. And okay, so it's really a technical proof, but it's convex analysis. I don't want to get too much into this. I can discuss with Rida. Maybe you have good memories of it. When we were young, we were doing a lot of convex analysis, but you broaden your scope. I did not. I'm still stuck to convex functions. Okay. Do I still have something like 5 minutes or 2 minutes to show you a picture? Okay. Okay. So, Marwan, you have a question? Or no, you were just stretching your arms. Okay. So to sum up, if there are moment constraints which make your life a bit more complicated in the framework of optimal transport, there is a qualification. I'm not saying it is sharp or whatever, but in the case of the martingale OT problem, it is very natural. And what was not known is that these two conditions say that the constraint is stable. Okay? When you tilt a little bit, the mu could be also done at the level of nu. There still exists martingale. The measure remain in the convex order. Okay? Now I want to show you one. Okay, this I will skip. Unless you insist. Okay, I want to just want to show you an example. Yeah, this one. Okay. Okay. What is nice in optimal transport for nice cost in 1D? Well, that's what you saw in the class this morning for the distance squared or convex cost or whatever marginal submodular cost, there is a distinguished transport which is optimal, which is monotone. So it's deterministic and it's monotone. For martingale OT, you see, you cannot be deterministic. The only, unless mu equals nu, there's no martingale which is deterministic. So that pi x is Dirac mass. You have to split the mass. So the sparsest kind of transport plans you can have in dimension 1 or in dimension is something which splits the mass into 2. And so that the center of the mass which is at x, the sparsest kind of martingales with prescribed marginal you can have is something which sends the mass of x to 2 points. The Dirac mass at t of x and the Dirac mass as s of x. Okay? And the remarkable papers, there was some competition at that time between Nizar and Nicolas Juillet, I think, but they more or less at the same time they issued nice papers to read, which you are reading by now, right, Marwan? We identified a class of cost for which optimal martingale OT has a simple sparse form consisting of 2 branches, which you can compute by hand. It is called the left curtain construction. It was called this way by, I think, by Juillet, by Goldberg, Tuzi. I don't remember who get the name, but they more or less get this. So now I want to show you just an illustration of what we have done. Okay, we introduce a parameter t between 0 and 1. There's a crazy cost which is here, but think that t is 1. So if t is 1, this is a quadratic cost, nothing else, with marginal constraints mu and u. So the solution is just the monotone transport, a single map which is non-decreasing. Now, if t is approaching 1, if t is approaching 0, this guy can be neglected. So, okay, it seems complicated. This is a problem where I want to deform for t equals 1, I have vanilla OT. I know what's going on. It's a test for numerics. But for t is approaching 1, no, for t approaching 0, sorry, this acts as a huge penalty. So you see that t approaches 0, but forces you to be a martingale. And this cost satisfies the condition under which the left curtain is optimal. So it's a martingale OT problem for which there will be 2 branches. So we like this problem, and the fact that the numerics, the kind of numerics we do, and the kind of continuity with respect to t and so on, is fully guaranteed. I want to show you the deformation of the optimal plan. Of course, we had a little bit of entropy to use synchron kind of methods, which is this, and it's pretty convincing, right? Because you see, in the end, so this is vanilla OT, this is the optimal transport, this is a graph. It is a bit blurred because of the entropy. But in the beginning, you see the left curtain with a branch. It survives, and it disappears after some time where you have this thing. So it's, I think it's, when we showed this to Nicolas Juillet, for instance, he was happy to see the deformation of this problem to the other. So I think it's time to stop. I'll be happy to answer questions. Thanks.